start. I don't want to diminish your time, so we have the second lecture of the Majorana series of this year, and please.
Okay, so yesterday we went through like cosmology 101, so we concluded on this slide, which was essentially sort of saying, well, all right, we promised to do something back in the selection time, back in '96, after studying 3 years for that mission, and that's essentially the basic result. Now, I want to, before I sort of look at what you do with this result, I thought that I will show you a little bit of Planck in the making. So the machine is this one. I don't think you should have this.
Sorry,
yeah. So essentially, the machine we built to do this after, quite a long time is this. So you can see the size of the object, and that's a 1.8 meter telescope. And this is a primary mirror, secondary mirror, and the focal plane is there, and all the rest is just a support mechanism. To sort of have a slightly better view, here it is. So this is a cutout, and so here is the focal plane with the low frequency instrument led by Reno Mandolesi de Bologna, and our instrument, high frequency instrument in the center. And then the rest is essentially helium tanks, solar panels, V-groove to isolate the cold part from the hot part. Now, of course, the very center of all this big machine of 4x4 meter are these tiny little things which are about a couple of millimeters, because this is millimeter radiation, which are the absorbers of the radiation. These are these are the absorbers, so this is opaque. And you have in the middle a small thermometer. And so that's when the photon hits there, it hits the temperature, the temperature picks it up, and then there is a drain so that the temperature goes back in the absence of a new impact. And that's for polarized radiation. You have actually two grids just separated slightly above one each other. So one direction of the electric field goes in that direction. So it deposits its energy in this way. So the transverse one just goes through and is picked up by the next layer. Okay, so that's, and these were created by, in the team of Andrew Lang, the guy that did if you remember, the experiment was Paolo De Bernardis that found that, we are in a flat spatial geometry for the universe. But then, so these things are actually there, and they are sitting at 0.1 Kelvin at the end of a back-to-back horn. So the radiation, the photons come, they have been traveling for 13.8 billion years, they got there. They are selected by a filter there, so if they are not around, say, 143 gigahertz, they are rejected. Otherwise, they deposit their energy there. And all the rest is just, these things are the cable that go from the 0.1 K that of course needs to be very deeply isolated from the rest. So all of this is just isolating from the rest, and then I forgot, and that's also in there that you mix the helium-3 and the helium-4 to create the final stage of cooling to the 0.1 K. Okay, so that's, so there are essentially 52 bolometers in there. So this is a real instrument as shown in the lab. And now it's sort of, I will build the thing from inside out. Let's see, does this work? Well, not always, so let's see whether it does it. Well, so let's see whether I can do this. Yes, I agree. Yes, you can access to this. Damn it. New protections all the time. So it used to work just with the previous version perfectly, and of course, well, if it doesn't work, désolé, nous ne pouvons pas lire le fichier multimédia. Okay, that's progress. Anyway, so that's the center. This is about that size, and then you build the satellite out to progressively provide all the services that are needed. To do this, we had to assemble a pretty large collaboration because, again, when we proposed that, Europe was by no means a leader on these type of things. And so, well, you can sort of see all that contributed, including very large facilities like in Liège for testing the whole satellite. And of course, I'm not forgetting the balameters are coming from the US. So after quite a number of years, Planck is finally in Kourou in French Guiana, ready to be launched after essentially 16 years of work. This is how it happened on May 14, 2009 in French Guiana. So I guess the next one will probably not work either. Let me just still give it a try. Oh, all right, so that's the launch. So this is really an interesting thing that happened because you are there, you have 16 years of your work there, and then you have essentially this explosion. It's because this thing is essentially about 220 tons of powder, these boosters. So they just put the lighter on 220 tons, and you just hope that this nicely progresses, okay, on the way. And when it starts, I'm not giving you the full story, but when you start, you feel in your body the sound wave. I mean, it's just boom! It's just amazing. Anyway, so it keeps going. Well, I don't know whether I can, let's see. Okay, no, I want the next. Okay, so this was the launch that was done on an Ariane 5 with the two big satellites. A lot of Europe science, space science was at stake because it was a very big, so Planck is there, and this is actually Herschel. And Herschel was a large mission. I mean, Planck was actually a medium-sized mission. So it was the most expensive payload ever of ESA, and you might not know, but it's not insured. There is no way to insure it. So it goes away, poof, you've just lost everything. Really cool. Then you go to the Lagrange point. Damn it, what is this thing? They just introduced, I mean, I never saw this. I've given talks like this before, but well, so just, can I have it? All right, well, too bad. So, well, this goes all the way to the L2 point of the Earth-Sun solar system, which is like, so here is the Sun, here is Earth, so 150 million kilometers. And now you go 1.5 million kilometers away, and that's a quasi-stable point. And then there is an orbit there, and so you orbit around that point. And that's your observing station. And of course, you will know that, of course, this goes around the Sun in about a year. And so if you have a scanning strategy, which is essentially nearly great circles, nearly 90-degree opening angle, not quite, 85. Countless discussion for this 85 number. Then you essentially, you can sort of see that once you are doing this, you have essentially covered the sky in 6 months. Not quite, because it's 85 degree and you're actually modulating the pointing axis, but that's pretty much what it is. In the process, while you are going from Earth to this Lagrange point, you are cooling the system, and by the time we arrived at the Lagrange point, we were ready to go. And let's see, can I get this? I think it's this. All right, well, too bad. I just don't want to spend more time than necessary on this. So this is a sort of the last image from the little camera on Herschel. This is the last thing. It looks like Darth Vader. So it has still the cover, and the lid will take off, and then it's going to be ready to start observing. So you can sort of see that this is a rather complex machine with a lot of thermal stages. So you start essentially at 300K, and then the top bucket goes down to essentially 50. So by then, the next stage can start operating. So you get the 20 stage, which is provided by the US from Caltech. And then it goes down. Then you can launch the 4K cooler that comes from Britain. And then once this is ready, and it's over, you can start the 0.1K that is provided by France. So all of this is really like international thing. And of course, so by the 3rd of July, we were at 93 milli-K. So this was a big thing to make sure that this whole thing would operate in space. I mean, you cannot just get out with your screwdriver, right? I mean, it's 1.5 million kilometers away. Now, this is the result of the success of Planck. This is it. What you see here is essentially on the red thing is just closed. You look at, you have a dark bolometer and you just monitor the temperature on the bolometer plate. And look at this. So this is day 90 after launch, so that is arriving there, all the way to the end of operation. So you see like there are 900 days. That's the long duration. And you see that this is at 0.1 K. And if you look at the scale, this is 0.1 milli-K. So this is really stable. You are better than 1/1000th of the operating temperature. So 0.1 milli-K over the full duration of the mission. You cannot get there anywhere apart from essentially the Lagrange point. So that's what I was telling you. It's an uber stable environment in which you can use these bolometers to actually do those measurements. Of course, it can be accidents. You do something, you operate something on the satellite, that it will ripple all over, and you have to understand it and so on. But I'm not going to get, even though we spend a lot of our time on doing these kind of things. I mean, this is not for this audience. Now, this is pretty much how Planck scans the sky. So this is a circle, but of course circle in this projection. And you can sort of see, I mean, progressively we saw, well, essentially the sky happening. And so you see the date on the top. And so after 6 months, roughly, you start having nearly full view. And then you start doing it again. And so initially, we needed to cover, that was the design. We asked ESA to be able to do it, to cover the full sky twice, so that we would have a minimum redundancy. We were very fortunate because we could operate our high frequency machine, I mean, well, actually the cooling, the 0.1, at the lowest helium consumption. And so we actually succeeded in pulling out 5 surveys. So we greatly, so not only we were able, of course, to increase the signal to noise, because it just, well, it's essentially square root of the number of surveys, but the redundancy is actually your best weapon to go after systematic effects. And remember, we are trying to measure things at the micro-K level. So there are lots of potential source of systematics from cosmic rays, from thermal fluctuations, from electric pickup in the system, you name it. So that's the thing, that this is your main weapon from the data analysis point of view to actually go and sort out the various things, because of course, when you are coming back to the same pixel of the sky, everything is changed. For instance, you are scanning in different directions, it's on one side of the sun or the other, and plus the many other things in the system have changed. So that's your basic weapon. So logbook is essentially, you know, that's the kind of dark side. You have to have reports, an amazing number of pages, and you know, every day some things to ESA and so on. But by June we were happy. We had a complete sky coverage. So, you know, we knew that we had a minimum on disk. Well, actually the data is coming every day, so it's not on disk there. It's on disk on the ground. By November we had a nominal mission completed, which allowed us to do the first Planck release after some intermediate things in 2013, which we delivered the nominal mission, we just had completed, only in temperature. Then by January 2012, we had all the HFI data acquired. So HFI is the part which is at 0.1 K, 5 surveys. And in 2015, this is the data we delivered to the community, at least in temperature, all areas. And we did a preliminary release on polarization. And then last year, we essentially delivered everything with our quasi-final analysis. And I think that we are resubmitting the last 2 papers to the referees essentially now. I mean, this is what I was looking at my mail now. So we are really at the end. So last commands were sent, so you really turn it off and you say, you sort of see what, like in the movie. So this is a small computing center I built in my institute to be able to process all of this data and turn it into science. And it had some kind of special requirements, so I built that machine on purpose. So data processing, I just want to say a few words about this. In some sense, it's very simple. I mean, you know, we have physics, which is what we are interested in. physics is translated into the CMD sky, which is through, I mean, just look at Mukhanov book or whatever, or this is what I told you, the basics of yesterday. Now, of course, the CMD is just one component, so you turn this in frequency sky, which is different superposition on CMD and different foreground contributions. And after that, you scan it, and you get time-ordered information that you receive on the ground. Now, all the job is actually to do the reverse. From that, you want to build frequency maps from which you will do component separation to extract the CMB, and from which you are trying to extract physics. And so, in some sense, to be able to do this, I mean, you have to think that what you want is to write QI as a function of physics, and then you want to invert it, propagating errors properly, and accounting for all the effect of systematics and so on. And in the end, you would like to give error bars, but this is such a complex phenomenon that, you know, it's not a Gaussian distribution of errors on the sky and so on. So in the end, the only way to transfer the information that we've accumulated as a group of people working together for a decade and so on is essentially through numerical simulations. So we do simulations where we do this plus this all the way. So you do exactly on the simulated data what you've done for the real data, which is a huge task. And you do this hundreds of times. So the full mission, which is, you know, about 1 trillion sample, is actually generated hundreds of times and processed hundreds of times. And you do this several times because you cannot do this at first go, because this is a nonlinear process, it's TOI. So you solve it iteratively. You find a solution that allows you to clean the data, and then you find the next order prong. So then you solve it, and we did essentially 12 release. So, and 12, when I say release, I mean what I mean is every time you restart from the raw data. The only thing that you carry from one step to the other is knowledge, is a data model. So the difference is, you know, you've understood the data up to some level, so you can have the parameters, the abstract representation, which incorporate all what you've already acquired as knowledge, and you use it to do the next pass of processing and understand the next series of problems, and you do it again. And you do this about 12 times.
François, how long it takes to
okay, a cycle, a successful cycle is about 6 months. Some were shorter because we were less ambitious, because this is another thing that is of interest, which is, of course, there are some simple things, which is you do null test. Like for instance, you have one detector, another one, roughly at the same frequency. You differentiate them, so you have just a null map, and you can sort of check whether this is consistent with your model of the nodes. That is fine. But then progressively, you want to demand more of the data. So you start by looking at the physics you get out and see whether the physics, now you go all the way to parameters, and you sort of say, well, what if I look this polymer, well, this detector, or this set of detectors versus this other set? So now you do null test all the way to the final analysis. So this step of not only doing the processing, but actually having all the other part of the collaboration, taking the data, understanding the new thing, inventing a new analysis, and reporting, essentially to me, to say, well, this is where what is really bizarre. And then you invent how you should correct the processing. So that's why this thing, well, the actual processing is actually not that long. I mean, just the processing of the data, we actually used also, the longer part was actually when we started to need full simulation of the processing. In that case, we were using the NERSC in the US, which is number 3 to 5 in terms of supercomputer in the world, to actually do that. So all of these changes in the end, like 6 months. Okay, so the only comment I wanted to make there, which is there are lots of instrumental challenges in building the experiment, in operating it, and so on. But there are also quite interesting challenges in terms of data processing because, well, you have to balance optimality and speed, for instance. There are operations where you can write the inversion, if you wish. Well, inversion, if you're not careful, is just something that will scale like a very large power of the number of pixels, like n to the 6, if you have determinants and so on. For millions of pixels, that cannot do. So you will settle for quasi-optimal thing. You can then increase the processing speed, maybe by a factor of 1,000,000, but then you don't want to lose too much in terms of size, given the cost of the thing. So typically you want to lose optimality by maybe a fraction of a percent. So this is this kind of things which are practical applied math. And of course we had some applied mathematicians with us to help with this. Propagation of errors, of course, in the end you want to, if you are having a Bayesian approach, you will have a large dimensional leafy space that you would have to explore. So, it's easy to go 5, 6 dimensional, but as soon as you start saying 50 dimensional, 25 dimensional, 50 dimensional, well, it's becoming challenging. And yes, and something that is more on the management side, physicists are like cats, and so one has to manage a large cat, a group of cats. And this was essentially, people were gathering in my institute from all the planet every 2 months. And we did this for years and years and years. And, I had to sit in front of people, well, much larger group than here, and, you get the flag and you get there, you interact, and then you go to the next processing stage. It's fun. Anyway, so here is an example of what you do to just go to make a map. I won't go through all of these details, just to tell you, there are lots of, you see, there are lots of places where this interact, like, you do something and then, oh yes, you have better pointing, so you can redo everything and so on. So you have all of this sort of feedback loop and interaction loop, which of course requires that you solve this essentially by iterations. And the map making is just pretty much at the end. So, numerically, in terms of data, it's for the HFR instrument, we gathered about 1 trillion time samples. It's in about 100 timelines, not quite, counting auxiliary things, from which we extracted, you see that this is a factor of 1,000 contraction, 1 billion pixel values. And you might say, well, where are they coming from? Well, you have IQU, Q and U being the Stokes parameter, this is density, so you have 3 maps at 7 frequencies, and 2 maps which are not polarized, so that's 23 maps, and each of them is like 50 million pixels. Just like an excellent camera that you buy in the market. So it's, out of this, you do component separation, so you just get the CMB maps, so it's a little bit less, 100 million pixels. Do the harmonic transform, that will also do some compression. There are some modes that you are not interested, it's like 10 million. And in the end, the points that I showed you before, it's about 10,000 points. If you are not billing it. And of course, in the end, you fit this with 6 parameters, and it fits statistically in an excellent fashion. And more importantly, there is no significant evidence for the need to introduce additional physics, which will turn into constraints on omega k, or which will get into it. And that's probably maybe when it gets closer to today. And when I say most of the cosmological probes, you know that there are tensions like H0 and so on. So I'll walk you through this later on. Okay, so where are these products? So the legacy of Planck in terms of map, this is it. So 9 frequency map, the low frequency instrument from the LFI consortium is from 30, 44, and 70 gigahertz, and we created the 6 other ones. These are expressed in thermodynamic units, which means that something that has a Planck distribution is actually having exactly the same physical appearance, visual appearance on those maps. And clearly you can see it. Oh yes, I remind you that this is a galactic plane, and the center of the galaxy is here in these coordinates. So clearly you see synchrotron and free decreasing in frequency all the way to here, which is shown actually here. And then you actually, starting from here, you can start seeing the dust contribution that increases with frequency, that starts picking up all the way to the last two channels, which are entirely dust tracers. Okay, but on the other hand, when you are not screened by foregrounds, you clearly see, I mean, you see the same thing at high galactic latitude. So this is the background that we're all looking for. Now, of course, and WMAP was actually, which was previous, LFI is sort of an improvement over WMAP. The highest frequency of WMAP was 90. So all of this was actually totally unknown. And that was one of the dangers with WMAP, was that they were not sensitive enough so that for this to be really a danger, was the fact that they couldn't tell what was the dust contribution because there was no measurement. So you had to rely on some theoretical modeling and so on, and that was one of the limitations. Now, our most sensitive, I think it's, yes, the most sensitive channel is about this one, 143 gigahertz, and a lot of science relies on this. And what you can sort of see is what is achieved is the RMS of the residual, the detector noise if you wish, is 0.5 microkelvin degree, which means that if you average the noise into a 1 degree by 1 degree pixel, you get 0.5 microkelvin. And then, of course, if you increase the pixel size, the surface goes like a square, and so the number of modes goes as a square, and so you take the square root of this, so it linearly scales to this. So it would be half of this on 2 degree scale, and twice this on half a degree scale. So it's a very convenient way of measuring things. And the angular resolution is about 7.3 minutes of arc. And this one is at 5, and that completes the promise that I mentioned, that if you want to go all the way to the still depth, so you measure everything. Now, as a supplementary material, we created Q and U maps in polarization, and you can use that to get polarization, direction, fraction, and all of that. Out of this, well, of course, one thing I did by showing this, I already removed the dipole contribution, which is actually the dominant thing. Otherwise, you wouldn't see anything, but you saw it on the image I showed earlier of Kobe. And so it gives us a very high accuracy determination of deep dipole amplitude, to the point that now we know our speed as compared to the reference to, if things are all proper, it's 0.1, the precision is 0.1 kilometer per second. This is just pretty impressive, I would think. This is 0.025% formally accuracy. Now the next step is actually to use all of this information to extract the CMB part, and so that is also quite a bit of R&D, and we spent a lot of time on developing new methods on this. So we implemented essentially 4 methods, which are pretty much representative of the state of research on how you solve the cocktail party problem. The cocktail party, by the way, in applied math is when you put microphone into a cocktail party, and then, so they are separated, and you use all this information to be able to pick up one particular person's voice, right? So it's this inversion problem. And so you use everything, the frequency, as well as the spatial dependence of various types of signals to separate them. But of course, there are several criteria you can use to do this. I mean, just so you can ask, they say that within a model you have a minimal statistical residual, or you may want to absolutely bar some particular frequency dependence, and so on. So you may want to do this in several spaces, in real space, in harmonic space, in wavelet space, curved space. Okay, so that's essential. I don't want to get into this more and more because it could be easily more than an hour. But that's something where we put the 14, we assembled in the end 14s, and essentially all of the processing, all the science results were obtained using the 4 methods. And the idea is that there is not a method right. You're just optimizing for different questions. So in the end, when everybody agrees, well, it means that this is completely solid. It doesn't depend on how you ask a question. The data absolutely require that particular solution. When you get further down, in terms of weakness of the signal, then this is where the way you ask the question, you get slightly different answers. And so we thought that this was useful to tell the community, well, you know, at that level, you start being dependent on how you do things in detail. And there is not a right answer, which created endless debate in the science team because a lot of people, including the science team, had a little bit naive ideas. You know, oh, there should be the right answer of how the sky looks like. Well, no, with finite precision data, you cannot do this. Anyway, so in the process, you learn a lot of astrophysics. I mean, you learn about the synchrotron amplitude, the free, so these are full sky amplitude of components that has a particular frequency dependence. The spinning dust, the thermal dust, CO, which are line emissions, the Sonia-Zeldovich with various clusters, the cosmic infrared, and all of that. So there again, I mean, I think that Planck had a rather transformative impact on lots of aspects of astrophysics, in particular the interstellar medium of our own galaxy, which is, after all, the best thing, the best cradle we have to study star formation, which you may not know, but that's completely, we don't know yet how to form stars, because we have just the first idea of how you start collapsing, but then you have to go all the way to these huge density contrast, and that's not known yet. Anyway, so in the end, this is the sky map. And I made sure to show this part, which is actually just inside this. This is just in painted. There is no way to do with any precision. So it's just for visual purposes. But no I want to insist on this. No scientific analysis is using that data. Okay, and then you can have all kinds of refinement about how you apodize and blah, blah, blah. I mean, all of that is sort of data processes. Well, this, as soon as we release the first version of this, which is visually completely indistinguishable from this one, it was noted quite broadly. And I think I was particularly happy to see the cover of the New York Times. But we have the same, we had 2 pages in the leading French newspaper, Le Monde, and so on. And that was noticed in broad circles. That's something you may, it was fun to be invited to chat a little bit. So here it is. It's not very often that I'm having a jacket. Anyway, so again, I told you about temperature anisotropies. Now, Thomson scattering are polarized. So you see this little picture of how things go. Now you can sort of see obviously that if in 2 directions at 90 degrees, you don't have the same incoming radiation, well, you have a residual polarization outside. What if, in more technical terms, it means that you need to have a quadrupole, a local quadrupole at the last scattering surface. So as soon as you have different influx of photons locally, you create polarization. In which pattern? Well, that's sort of shown here. If you think that you have these acoustic waves, which are oscillating like this, so just think of something that is, for instance, a converging flow. And so you look in the reference of the electrons that are in the flow, and then you can quickly convince you of that, the type of polarization that you get, which is essentially radial polarization. And of course, a diverging flow leads to a tangential pattern. So now you can sort of see that naturally this thing, this quadrupole translates directly into the local E mode of polarization. So that's the Planck map on the smoothed on a 5-degree scale. So and I'll get back to this. So these are essentially the polarization vector on that scale. And for your perusal here, this would represent a point, say half a micro-K of polarization, that length. So that's how, the current state of knowledge about polarization, but that's not all there is. I mean, that was for graphical purposes that we show this at 5 degrees. In the back, sorry, I should have said that. In the back, that's the temperature anisotropies. And you can start, by looking at this, you can start seeing that this is correlated, which we'll, of course, measure more properly later on. But now, let's look at this little thing here, and you can sort of see that there is still a lot of signal to noise here. So that was purely graphical. I mean, it's not the end result of the data of Planck. If you keep doing this, again, you can blow it. So of course now, this is 13 micro-K. And so even on a 7 minutes of arc, So now we have some noise contribution, but there are still a lot of signal. So all of this was extra as compared to what we promised to ESA back in '96. So one thing you can do is actually start taking the peak or the trough of the temperature field and on the top of this put the polarization pattern, right? And when you do this, well, obviously if you have something like a peak or a trough, this was a place where you see the wave, the perturbation, and you do it like this or like this. So you expect to see this radial tangential pattern, depending on that, as I just said. You can, of course, simulate this. This is like something noiseless, and this is how it's seen by Planck. So the beauty of this is that you're actually seeing the dynamics at the last scattering surface. Not only are you seeing order 0 delta over rho or delta phi over phi, but you also see the velocity field. So the idea that we're mapping, at least on the shell, all the dynamics of the universe at 13.8 billion years ago, I'm just still excited about this, with quite a bit of accuracy. Well, I think I'm not going to go into the detail of this on how there are the various regimes because I'm thinking I'm a little bit late. But that was just, it's exactly as we expect. Now, this is something which is actually a high frequency map. And what you see here is a rotation of the polarization vector that shows actually the direction of the magnetic field. And so, well, this image completely revealed a new picture of how the galaxy looked like, but more importantly, it shows that there is essentially no part of the sky where you can neglect the dust polarization. And you may remember that there had been claims that there was a detection of the primordial gravitational wave by the bicentennial people. Well, of course this was not public at the time, but then, well, they essentially measured, at least half of what they measured was dust. And since this was like 4 sigma detection maybe, in the end it was at most, a 2 sigma detection. So, and of course I can tell you, further we kept working on this, and so there's still no sign of primordial gravitational waves. But what this shows is that it's going to be tough to go through the dust screen, the polarized dust screen, to actually go after the primordial gravitational wave, which is really the next big item in this field. There are lots of other interesting things, like neutrino masses and so on, but well, for people like me, this is the primary motivation to go is still, you want to see the tensor mode if it was inflation during the inflationary period. Now, as I also mentioned, photons from the last scattering surface have to travel through all the large-scale structures which are forming. Of course, at some point the universe will reorganize, and then the structure is formed, and you see this sponge-like topology that is progressively appearing. And what it means, and it's written here, what you observe in a direction is actually the primary one, but offset in direction by the deflection. So if you think of this, this is essentially given by the gradient of the potential, at least, well, the integral of this, the effective potential projected along the line of sight, right? So, okay, so we are not seeing exactly, of course, the last scattering surface. We see slightly perturbed in terms of direction by the gravitational lensing, which of course is a particular kernel. But now you can think of this, well, this is very small. These are arc minutes. So you can actually tailor expand this, and as soon as you do this, you realize that you can create a solution for phi. And so now you can actually, and what you'll be using, and I'll show you this in a graphical way the next slide, so we'll be able to recover what is phi and then recover what is t without influence of phi. Yes. So temperature, you suppose that this is the last scattering surface. Of course, this is a simulation. E mode, and you suppose that there is no B mode. Okay, the B mode, which are the things which are not scaling, not invariant in a mirror. And now, how is it observed? Like this. So when you do this, just have a So first of all, you see that this is a small displacement. Typically, this is like 2 arc-minutes. But more importantly, you see that this is actually correlated over large scales. Because typically you have big patches corresponding to big clusters or superclusters. And so you see a coherent deformation. And if it's Gaussian, you don't expect this. You don't expect scales to be correlated, right? So in other words, you say is you're breaking the statistical isotropy locally. So you can use this sort of say, oh, so now I know, oops. Okay, so now I know that if I correlate the small scales with the large scale, they'll be correlated as compared to the no correlation. And that's actually in a way that is a direct imprint of the phi field, and which is the phi, the projected gravitational potential along the line of sight with the kernel. Okay, so we can do this. Oh yes, so what it does, by the way, it's good. So what this does, it actually, the various peaks and troughs are actually smoothed a little bit. Just think of this as there are several images in different regions which are overdense or underdense. So you're actually shifting this thing as a function of the local curvature. So when you add them up, well, it's essentially smooth slightly the peak. It introduces, of course, non-Gaussianity. I mean, that if this is something that is not described, it's non-Gaussian, so that it has to be the next order. And one thing that is really interesting, well, really important rather than interesting, is if there was this deformation means that something that was purely an E mode is now also creating B modes. And these B modes are not primordial. They are not the imprint of the tensor mode. So on top of potential primordial tensor mode, you have the B modes generated by the deformation by lensing of the E mode. Yes?
Sorry, the distortion of the image, you observe at large multiples.
We observe that at all multiples. I mean, this is actually degree scale. If this is typically degree scale, and you are moving things by a couple of arc-minutes. So the displacement is very small, but it's correlated over large scales, degrees. Of course, this is something that happens essentially at all scales, right? But
no, for example, double map was not fine to observe this effect. This is an improvement that you.
Oh yes, I mean this is the premiere. I mean nobody has done this before. I mean this is the first sky map. Well, the next slide will be the first sky map. Yes, it's coming. So using this, you can create a map of the projected, the line of sight projected potential, gravitational potential, which is equivalent to essentially delta rho over rho. So what you are seeing is really an integral of the dark matter distribution, all there is, and so not the light this time. We're talking of the gravitational potential integrated along the line of sight. And what is interesting is to sort of say, well, what contributes more? Because you see the pass, you add contribution of various layers, right? So obviously, and lensing typically is most efficient for a lens which is halfway through the observer and the source, right? So you do this on several things, and the end result is that typically the largest contribution to this is a redshift around 2. Of course, there are contributions from essentially every redshift, but the primary contribution to this map is coming around redshift of 2, with a very broad kernel. So we are seeing essentially the imprint of all the dark matter in the universe in this map. So this one is really, to me, this is really the equivalent of the Kobe map for temperature. I mean, this is the first time we see it. It's actually going one step further. It has actually the same angular resolution and the same signal to noise than the initial Kobe map in temperature. This was smoothed so that you get the best signal to noise you can get, which is of the order of 1. And this is a scale which is about 10 degrees. So this is really, really very equivalent to the Kobe result. So it means, and I just told you, that's a signal to noise of about 1. And I'm going to stop here. is a good place to stop. So none of these features you can actually say, like on the temperature map or the polarization, yes, it's there. It has to be statistics. But then statistics is our tool, so we'll use this. And I'm going to stop this at this point. By the way, just for amusement, at this angular resolution, this thing that you may be recognizing, this is the angular resolution of the map, and with a signal to noise of the map. So, sort of a visual impression of what this map is about. And I'm going to stop here. Coffee time. And I'm still not done about day one. Damn it!
We will have a discussion session, discussion time this afternoon at 3:30 p.m. in 1G9, 1G09. So if you are interested, you can come.
What time?
3:30 p.m. Okay? So we can start with this second part of the.
Okay, so essentially, this is a projected distribution along the line of sight of all the dark matter there is in the universe, essentially, well, all the way, in the observable universe, should I say, that is all the way to the last scattering surface. Now, again, I told you this is essentially a signal to noise of the order of what? So how can we, we had to ask ourselves the question, how can we tell that this is not garbage? There is just no feature. So one thing we did was actually to look at the cosmic infrared background, which we isolate in several other frequencies. Well, these are actually, I told you, the integrated emission of infrared galaxies, which are, most of them are at pretty high redshift. So they are actually tracers, luminous tracers, of the dark matter distribution. So what we did, we actually stacked the deflection field around the peak of the tracers. And what you do this, when you do it when you stack the deflection field, we constructed a deflection field of lensing on peaks or trough, and then when we just stack at random. Well, that's completely obvious. So yes, even though that's no signal to noise, it's clearly we are actually mapping the deflection field, and so directly the gravitational potential. Again, projected along the line of sight. Well, you can actually do better. Since now we have some approximation of the deflection field, we know, so from T and delta T, we got phi. Now, having phi and having an E map, we can actually compute what are the B modes which are created by this. And if we had a direct detection of B modes, we could subtract that contribution to actually look at the primordial B modes. That's exactly the program of the future, of the ongoing experiment. That is, you want to actually have much higher angular resolution and sensitivity images in polarization. So you actually have a much better reconstruction of the phi field from which you can actually do delensing. That is, compute the B contribution that you remove from your B map to actually look after the primordial gravitational waves. So this is actually very low signal to noise. The reconstruction removes maybe 10% of the signal. I mean, it's just the beginning. But it's always the same. I mean, Planck is essentially the thing that finished the full temperature and isotropy thing. We advanced considerably the polarization, and we started essentially the lensing part. And so, of course, the future is in that direction. So now let's move. I told you the math. Let's go to the angular power spectrum. So I remind you, that's what I told you by waving ends, the ALM coefficients, it's just the harmonic transform. And what you know is that when you look at the 2 point, if it's a statistically isotropic field, it doesn't, only the L and M, the same L and M are cross-correlated. So you have the CL, which is the thing that we've been plotting, and now you can get an estimate of the ensemble average by just looking at the average over the M modes. Oops, sorry. Over the M modes. And very often what is actually plotted, as I already said, is this DL, which is the logarithmic contribution to the variance. So here is the actual determination of the power spectrum from Planck. L by L. So that's actually done in the power spectrum space. That is, you look at all the power spectra of all the cross between all of the frequencies, you implement explicitly a data model, and then you recover the power spectra of all the various contributions. Right? So that's Planck result. You can immediately, it's just for graphical purposes, we also change the x-axis between the large scale and the small scale, because we want to be able to see what happens there. And that's L by L. And you can already see that the dispersion increases when you go to high L. That's the noise residuals. When you beam, that's what you get. Okay? And just remind you what was the situation when we dreamed of doing that experiment. So you can sort of contrast this thing, which is a bump at L of 200 as compared to this. And of course, there was no data point. So now, this is a comparison to the best fit lambda CDM model. So, well, of course it fits well, but let's look at the residual and the 1 sigma line. So you can count, there are 66% of the points which are indeed within the 1 sigma line. And you see that the residuals are actually tiny. And if you go, this is a 6,000 micro K square, and now you're looking at the residuals, we are in the few micro K square level. And there is essentially nothing that is really visible, with one exception, which is also completely obvious, which was not discovered by Planck, that was already assigned in COBE, and that was already in WMAP, but there were questions, is this thing, L of, say, 20 to 30. You see that there is a clear deficit. But what was known, there was a low quadrupole that was from COBE times. And COBE had these points, essentially. That was the points of COBE. That's this all the way to L equal 10, roughly. So there was this low quadrupole, that was countless papers. Now, this was noted, and what Planck brought was the fact that we were using now a different technology, so this has nothing to do with particular systematics or whatever. We're also covering a much broader part of frequency, in particular all the high frequency. It cannot be dust, it cannot be any of this, so this is really on the sky. Now, unfortunately, this is a pretty low statistical significance, it's roughly 3 sigma. And so it's one of the rare signs we have that maybe there is a break. I mean, there is a feature in the primordial power spectrum, maybe. But it's low significance, and I'll get back to this. That's one of the rare hints we have of something further than lambda CDM. Now, essentially, you can also see that, okay, that's cosmic variance. That is, you sort of see that things decrease with the number of modes. Well, square root of the number of modes but that's a square, so it's clear. And you see around here, the scatter starts to increase, and that's precisely the nodes. So you see that this is becoming, the minimum is here. So essentially, it's a cosmic variance limited measurement all the way, to 1600. Oops, where is that? Okay. And WMAP was limited about here. That's give you some point of comparison. So I went, yes?
What is the 1 sigma line? Is the 1 sigma of the model parameter?
No, that's really when this is a diagonal of the covariance matrix of the C minus CL model. Okay, that's.
So it's something of imprinting. It's independent from the error bar of the.
Yeah, I mean, when you do the likelihood analysis, if it's Gaussian, it's essentially the exponential of, data CL minus model VL, okay, transverse, covariance matrix minus 1, data minus model again. Okay? So, so that gives you essentially the dispersion as compared to the model. And so if you look at the diagonal part, you forget about all the correlation between the various L's and so on, which are present, then that gives you this. Of course, there are correlation because there are no correlation only if you are full sky, but we cannot do this, so we have to have a mask. The mask, think of it as just like a filter, and that filter correlates to various scales, and so that complicates the analysis. But that's, I didn't want to get into this. But anyway. So here is a reminder of the 6 parameters from lambda CDM. As you know, there are 3 parameters to get the dynamics, and that's essentially omega baryon, cold dark matter, sound horizon, which is a distance traveled by an acoustic wave, all the way to the last scattering. The optical depth, which is a non-fundamental parameter, which is just a way to represent the fact that we're transferring somewhat the signal by the light of the first object that formed, first quasars and galaxy that reionize the universe. So there's an optical depth corresponding to this. So that is something that, in principle, one day, if we were to understand this full process, we could actually derive it from first principles. We are very, very far from this. So in practice, you determine tau and you tell this to people that are trying to form galaxies and objects. Well, here is the integral constraint on the optical depth. It's actually reverse. And then, of course, the characteristics of the power spectrum model of the primordial power spectrum. Slope, sorry, it's a slope, of course, the logarithmic slope and the amplitude. Now, this is essentially a pictorial view of what you find in the Bouchet book or the WHO and whatever review. It's essentially how different parameters can be read off on that plot. And maybe the simplest is just the amplitude. Well, of course, if you increase the amplitude of the primordial spectrum, it's a linear transformation. So you just increase all the spectrum. Now, of course, NS, which is the logarithmic slope, well, it sort of tells you, I mean, you are just shifting the orbital pattern, right? So that's also pretty easy to see. The baryonic abundance translates into the relative amplitude of the odd and even peaks, and that's because when there is also, it's not only the imprint of the potential well, you have also the Doppler effect that comes in, and that's actually how these two are shifted as compared to the other that results in this particular effect. I don't want to get into the full thing, but in essence, well, that's the readoff. And you can sort of see that with all of these points that we have, and only 6 parameters to place with, this is not too degenerate a process. There are some degeneracies at some level, but degeneracies which were really present at the WMAP time due to the fact that you're adding this information, that is adding constraints in terms of L range, means that we broke quite a number of the residual degeneracies, but they were still left, and that's why we're using some low redshift additional probe to break those degeneracies, and I'll talk to that later. Well, let's meet. Yeah, I should have put this way before, but that's, you know, typically the E patterns and the B patterns that I alluded to several times about being, you know, the type of patterns of polarization on the sky. Now, so here are the power spectrum, the equivalent of the previous plot. Now, for the E mode, here, and the TE, the cross correlation of T with E. And the remarkable thing is that this blue curve here is a prediction. There is no parameter in this fit. It's a prediction within lambda CDM of using the parameters that were fit on temperature. That's a perfect prediction. There is just statistically nothing you can see. So it means that this is a pretty good predictive model for polarization. Of course, once you've done this, you can co-use 2. That's what we do also. And that will help us to actually go further into non-lambda CDM models. Now, this is now the lensing power spectrum. So this is equivalent to 4 point. I told you the phi is actually cross-correlating the temperature field, for instance, at two different scales. So this is like a two-point function. And of course, the power spectrum, which is a two-point function of 5, is therefore a 4-point function of the say temperature or polarization field. And you can actually do all the combination like T, 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 E, T, E, E, T, and so on. So this was the first time that the lensing power spectrum was measured with higher accuracy. And now in the latest release, we detected this contribution even using polarization alone at 9 sigma. So now you can recover the potential field either with temperature or polarization in both cases, and consistently this is obtained. Let me skip this. So that's essentially how we get to that point, which was sort of the end of my first lecture. Well, let me see. By the way, the best determine, by the way, using this model, you can also forward predict what would be the Hubble constant today. And so you get something like 67 kilometers per second per megaparsec with a 0.8% accuracy. This is pretty high accuracy. Okay, now I will pause for a second about what is, I mean, these 6 parameters based on the ACDM is pretty amazingly minimal. I mean, when you think of everything that it describes, both in terms of number of points, but in terms of phenomena, all the way to being able to predict through numerical simulation the pattern of large-scale structures, all I told you about the sponge-like topology. So all of this is described with high accuracy with this very simple model. But again, I think this is important in particular for the student to realize that there are all kinds of implicit assumptions in the model that we have to sort of really recall. First and foremost, maybe physics is the same throughout the observable universe. It's not like, we just have a funny representative locally. GR is an adequate description of gravity. Otherwise, you wouldn't be able to do anything. It's all perturbation theory in GR. On large scale, the universe is statistically the same everywhere also. Well, of course, this is within the framework of the hot Big Bang. You have the basic components with dark matter, dark energy, baryons, photons, neutrino. The curvature of space, it hasn't demonstrated yet, but I will do this. It's very small to the point it's dynamically negligible. So it may still be there and it be of tremendous importance because geometry is different. But still, it does not do anything to the dynamics. And then, of course, for maybe this audience, most important is the variation in the density were laid down everywhere at the early time in a Gaussian, adiabatic, nearly scale invariant, but not quite. And so I'll sort of revisit quite a bit of this now. One thing I want to insist, though, is the fact that temperature and polarization are actually two independent views of the same early universe. And what we find is this model, which I represented a little bit facetiously like this, I mean, we recover the same thing. We end up deducing the same physics, which I think is nearly from the nearly philosophical point of view is really important. By the way, it's also consistent with lensing. Now, so I gave you the gospel of the standard model ACDM. So now let's look at the extensions. Well, the number of things which I already suggested that we want to look at is, are there some features in the primordial power spectrum? It's consistent with the power law, but can we find hints of anything that is not a power law? Like, for instance, this Lowell 20 band. Is there a tensor component? Isocurvature, primordial non-Gaussianity, and then checking bases and so on. So let's go to it. So first, since this is a linear processing, essentially, you can actually take the CL and actually deduce the P of K, because given that you've measured with great accuracy the parameters, you know exactly the kernel or the convolving function, so you can actually invert this. So here is the P of K. You can think of this as just instead of having another way to think of this is instead of parameterizing the power spectrum, the initial power spectrum by AS and NS, just think of the value per beam of P of K. P of K1, P of K2, P of K3, and this is just a smooth version of this. So if you have only two beams, okay, well, of course, you can only have a slope. And what you find at H sigma that this is not ns equal 1, which would be horizontal. You do see the fact, I mean, essentially, which can be interpreted as the end of inflation. ns is not equal to 1. You can sort of see that this is 0.96. And you see that this is 1 and 2 sigma contour, so we really nail it. Now, as soon as you give 3 beams, you can start seeing that, well, we have less well-determination at low L because we're essentially running out of modes. And here, because, I mean, essentially our beam, we're not measuring things with great accuracy. You do this at n equal 4, you can start seeing the L of 20. N equal 5, 6, and then, well, you can do this all the way to 9. Then you do a Bayesian analysis where you weight the evidence you weight each of the determination by these respective evidence, and this is the best determination. In the end, there is no significant deviation. So you recover with no a priori about the shape, apart from the fact that this is regularly smooth. You have to state that. You recover the primordial power spectrum P of K. And now you can look, by de facto, by doing this fully self-consistently, I'm de facto marginalizing about the effect of cosmological parameters. And so now you can sort of judge the L of 20 dent, here, L of 20, that you saw, which was very impressive. When you look at this, I mean, you know, this is like 2-point-something sigma. So it's not, when you account with the flexibility offered by the cosmological parameters determining the physics of the acoustic phase, well, that's the strength of the evidence. So maybe we have a clue about the early universe, but that's a weak one. That's just a fact. By the way, here are the determination of the power spectrum versus time. So this was Kobe, pre-WMAP, WMAP, and Planck. And really, even at WMAP times, I mean, the indications that it was different from one was pretty weak. And actually, as soon as you were to release any other parameters, the evidence in WMAP would disappear. In Planck, there is just no way to escape the fact that this is not scaling variant. Yes, so, all right. By the way, you can sort of see that this is, as many other things, I mean, many things have been determined with a factor of 100 improvement as compared to the early days of the CMB by Planck. Now, of course, you can go for specific models because when you do this in bin version, there's no way you can capture really localized features. So it's very hard without assuming a particular feature, but what you can do is precisely you can say, well, let's suppose I have a potential like this, you know, like axial monodromy, for instance. Well, we were talking about Einstein yesterday. So you can actually look at those. Of course, you're increasing the number of degrees of freedom, so you will obviously fit a little bit better. But then you ask, how can these be done by chance? So you look at the look elsewhere effect, if you wish. So you do simulations and so on, and you say, well, how often will this happen by chance? And you see that there is essentially none. So there is no indication in the data that you improve the fit substantially well to warrant the introduction of a more complicated model. Of course, we can formally exclude it. We just say that it does not improve the fit well enough to be worth, I mean, this can be, a small improvement could be only by chance. Could be due by the simple act of, you know, of statistics. Yes, well, same thing. I don't want to spend too much time. So now R. Okay, so now I introduced yesterday the fact that we want to look at the tensor models, which are measured, the way we parameterize this is by the tensor to scalar ratio, R. So AS was the scalar amplitude of the power spectrum. So you have the same thing. You would write AT, a tensor, times K to the power NT. Right? And NT is predicted also in a model. So in essence, what you're writing here is AT, amplitude of tensor mode, over AS, amplitude of scalar mode. So here is Planck, essentially. You can sort of see the constraint according to the use of different things, including when you use BK15, which is the bicep KEG measurement of 2015, the latest. And so you see that we're in this region. So you see this is the tilt and S. Now when you add this tensor to scalar ratio as an extra parameter, you see that you open that space, but there is no way to go back to the scale invariant NS equal 1. So we are there, and you can sort of compare. That was when you want to do the direct comparison with different models. Well, here are the locus of different models of inflation. For instance, if you look at polynomial models, you see that the archetypal V proportional to phi square is this one, and this slope here is just due to the number of inflationary e-folds. It's completely excluded. So the most basic model of inflation is actually excluded at many sigma by Planck. But then, of course, there are plenty of other models which are completely acceptable. And for instance, R square or Starobinsky inflation is securely inside what is completely acceptable. And some models like natural inflation, most of it is excluded, but there is some region which is still okay. So, and for this, it's, by the way, I mean, we've measured, it's important to realize that this measurement would tell us what was the scale of inflation, the energy scale. So for now, we can only say, well, V star is of the order of 10 to the 16 GeV in units of R equal 0.1. And for now, the best limit is R is 0.06. So it's somewhat below 10 to the 16 GeV. Not very much, because this is the fourth power. So it's very hard to increase considerably the constraints on the energy scale with this measurement due to this fourth power, of course. And something that was really important on the theory side was that then, if you are thinking of what this means in terms of potential, these are the line delimiting convex versus concave. So that's, and for this interpretation is both that during inflation, both phi dot square and phi dot squared over rho are both increasing during the inflationary period. So this is directly related to sort of pretty generic features. Yes, well, I'm just saying the same thing. I mean, you can classify in these, the various, because again, I mean, we cannot, there are a slew of inflationary models. So the thing that you are trying to get are really generic things that are really informing you about general features. So that's why crossing this line was pretty important, that we are in this regime. So generically, all models which are acceptable have to be of that type. And so potentials typically with this flat part here, which is, and then you have all the open questions that where all the thing with Steinhardt and so on. Why is it that you would start in this and roll down? And so all of these are open questions in theory that you guys also maybe. And then you can run Bayesian evidence of every single field slow roll model of inflation, rank them according to the various evidence and so on. So I mean, there is a full industry on this. This is a cosmic controversy I mentioned, and I just want to remind that they claim all of this, in particular what sets a proper initial condition, and yes. Yeah, I mean, we agree that to some of this, but that doesn't mean that inflation is in trouble. It means that, yes, we have still a lot of work on the theory side. But that, yes, there are mysteries, but that, I think that they were really pushing their point a little bit too hard in the way this was done. And of course, this was not addressed to professionals. That was done for Scientific American. So this was really addressed to the general public, sort of say, well, all of these things that some scientists might be telling you are actually just, not serious, which was maybe a little bit pushing it. Now, something that, I'll do in this plot, which, we'll start looking at essentially all of these extra parameters. So these are the standard parameters, and you can pick up instead of using, it's convenient to rather use the sound horizon, theta, to use h naught, which within a model is equivalent. So here are standard parameters, and the standard value in the lambda CDM are essentially along this line. So the values that I gave you were when it's assumed that omega k equals 0. Okay, so what you see is actually the projection of the acceptable regime when you open that parameter along that line. It will marginalize over that parameter. So what you see, so you can do this, it's a one-by-one exploration. What if I open the curvature? What if I open the equation of state? What if, and so on. So I showed you already R, the case for R. And there are already things that you need to look at. Can I have a, yes. For instance, let's look on the impact of NS, since this is so important in the predictions, of opening R and the curvature. And what you can sort of see is, oh, by the way, I mean, let's say, and I should add, let's look at pre-WMAP, WMAP, and Planck. So when you look at, with WMAP data, it was completely degenerate. And NS could very easily, as soon as you were opening curvature, NS could be 1.04. That was completely consistent at the 1 sigma level. Okay. So, WMAP needed to assume on the ACDM to be able to say anything, I mean, to be along this line. In other words, it was not robust to the assumption you were making about, extra degrees of freedom. Now, when you look at this generically, you see that a lot of these degeneracy lines are completely broken when you get to Planck. And for instance, omega k, look at how it's, the Planck determination is there. So it's becoming a lot more robust, if you wish, to do this. So let's focus, for instance, on this. So here it is. So you can sort of see better what I was just telling you about. Whoops. This is another one, and this time this is more about neutrino physics. For some of you, this might be of interest. When instead of assuming that it's essentially at the lower limit, 0.06 eV, and when you are not assuming that the number of degrees of freedom is not the standard 3.04 value 6, again, you sort of see that this degeneracy line that goes all the way to NS greater than 1 is actually broken by Planck. And this is just adding this extra constraint at high L. I mean, this is nothing else than this. So if you look at this again, you can sort of see it. So you can see that 0.04, 1.04, I mean, it was quite in the 1 sigma. And so when you do this, you can sort of then turn these upper limits that we have on, say, sum of mu. In that particular case, this is 0.245 eV. And if you add some extra data now from low redshift, this is not Planck alone anymore, then you get down to 0.12. And I intend to have like 4 or 5 slides on neutrino physics later on. I don't know whether I will ever get there, but okay. So I think to sort of summarize this, in short, the departure from scale invariance is actually now quite robust, including non-standard neutrino physics. And the determination is always at least 3 sigma away from 1, irrespective of the extra degree of freedom that you are throwing at it to put the constraint, or at least in all of those that I showed. I mean, maybe you could add still something else. So that translates into this constraint. I'll get back to this, so let me skip to this. Isocurvature. Okay, so I told you that there were not only adiabatic modes, and it could be isocurvature modes, but isocurvature, since there are several fields, there are many ways to compensate with zero curvature total, but to have a fluctuation, a local fluctuation in one fluid being compensated by one of the others. So there are different types. So you could, and there are, depending on what you are varying, as compared to radiation, because the dominating field, of course, is radiation. So you could have cold dark matter versus radiation, or baryon versus, and so on. And you can even have some mixed around this. Yes, I'll try. In the end, this is essentially, the non-adiabatic component is essentially completely constrained around 0. And you can sort of look at how much we've progressed in the recent years. The WMAP data, for instance, 9 years, are this green curve, and you see how much this is collapsed by the introduction of the Planck data. So again, there is absolutely no indication for isocurvature modes of all the types we've looked at. There are many models, so it's just to sort of tell you, if you want to have all the details, you have to look in the papers, and that summarize all the, you know, the models we explore, that they are all constrained, the constraints are given. But the thing that is important is, if you look, when you open all of these degrees of freedom, you want to ask, well, what happens to all the rest? Because in principle, you could have degeneracies, which is when you open that Pandora's box, maybe H naught or some other values become completely different. Well, look at H naught, how stable this is. Whatever you throw at it, these extra parameters, these extra degrees of freedom, you find that the CMB really wants around 67 kilometers per second per megaparsec. We'll get to this, but that's anticipating. I'm anticipating this. I'm sort of telling you, it's not going to be the solution of, oh, what if omega k is different from 0? Can this change? I'm just telling you already, no way. I mean, this is, the implication is, even if you open these degrees of freedom, these basic parameters there are actually pretty securely determined, at least within this whole class of models. Now, so it's actually an interesting plot. You can sort of think of this as an exercise in reducing the acceptable parameter space. So you have, like, if it's a 6-dimensional model, 6 parameters, so this is a 6-dimensional volume, and you are bounding where what the data tells you about where the parameters need to live, in which subspace, which doesn't have to be simply connected, by the way, but that's a different story. So for long ACDM, you can sort of see pre-Kobe, we normalize it to 1. The way this is done, you look at the covariance matrix, which is the full object, and then you look at the determinant, and so this is essentially the product of the, say, 1 sigma value, the eigenmodes, and so that really gives you some idea of the acceptable volume. And so pre-WMAP, it was actually pretty good. I mean, you know, already just the fact that it was found that omega k was around 1, there was already quite a bit of compression. Then WMAP, the final result is here, and then you see Planck, just 3 years later, the further constraint. And what you can sort of see is that, you know, for long ACDM, this is a 10 to the 10 improvement in terms of volume of the parameter space. And that's a 6 months doubling time in 26 years. So, I mean, Moore's law is, as compared to cosmologists, I mean, that's peanuts. Well, I'm joking, of course, but, you know, so we had a 6 month, not 18 months, 6 months doubling time in terms of constraint sustained over 26 years. So that's pretty extraordinary. And so, for instance, it's in the 5 years from WMAP 9 to Planck 18, we've reduced the allowed parameter space by a factor of 100 million. So that gives you some idea of how fast we collectively progress in terms of constraining what models are acceptable to describe the actual, you know, the sky. All right? And of course, you can do this for different type of models, including, and the higher the dimension of the model, actually the more impressive is the contraction. So models where you actually not only construct lambda CDM, but you also want to measure, to open simultaneously, not the one-dimensional one, but all of them together, and then you can have even a further reduction of the allowed parameter space. And, well, I don't know whether I'll get there, but I also made that plot also for the future generation. And I can already tell you, this is not the end of it. We will, if anything, continue at the same rhythm if we, for reasonable, if the money flows sufficiently early, it's not in the next century, we can actually go all the way to there, the cosmic variance. There is a lot more, another way to say this, there is a lot more information that we can grab with the CMB. Non-Gaussianity. All right, so I'll try to do this. I really want to finish this today, so that, okay, 5 minutes. Well, you already know, I already mentioned all of this. So, primordial non-Gaussianity, you have whatever is your inflation field, you suppose this is a phi field, translational invariance and so on, so it only depends on the modulus, and you have to have this delta thing, and you model this as a dimensional thing plus a shape parameter. And the specific model will give you a specific shape, it turns out that general single field models of inflation are essentially described mostly by two shapes, which are the equilateral shape, this is given as functions of k, or the orthogonal shape, which are just, when you say shape, you can actually plot as a function of k1, k2, and so on, and then just look at the functional form. And then there is, and so what we can do is sort of say, well, let's assume a particular shape, and let's see what is the maximum allowed value of FNL, whether we detect something non-zero or not. Okay? And then more complex models are can be captured more with a local shape, which is given here. So these are the three what I will call LEO, like local, equilateral, orthogonal, which are actually pretty generic, but of course if you have a special model like DBI or whatever, it would have a very specific shape and we can actually go for that. But then the space is nearly infinite. So, yeah. Of course, this particular shape, these are the shape factor in K, which I was just describing. They translate into a particular, through the linear evolution, into a particular shape into L space, which is the space of our measurement. This was in the K space. I mean, now this is what we observe on the sky, that is the L modes. Right? So we are actually trying to measure the three-point function of the, say, temperature or E-mode field or whatever, and then to infer this. Of course, there are specific shapes due to specific models that you guys can produce. Now, to give you some idea of what this is, so for instance, for an FNL local, if you take a map like this and you have a very large variation, you see that essentially it's a third order moment. Third order moment, so that's skewness. This is the asymmetry left versus right. This is the asymmetry between cold spot and hot spots. So when you have values of say +5 or -5, you see that you enhance as compared to something that would be symmetrical, the cold or hot spots, right? Now, let's look at something a little bit more expected. This is FNL of 0, and now you see if FNL equal 100, how the visual difference. There is essentially nothing we can see. Essentially nothing. Now, you will then realize, when I tell you that the upper limit and 95% confidence limit in Planck is 10, what we're talking about. You have to really, I mean, this is things that, so people are sometimes saying, oh yeah, you don't do all the analysis blind and so on. This is completely ridiculous. I mean, how can you tell anything? I mean, this is a factor 10 times higher than our upper limit, and you cannot see anything. So you can build optimal estimators, so that's something that I talked to the lady there. I mean, it's pretty simple. You can sort of just say a minimal variance estimator of the coefficient of the three-point function. You do this, but unfortunately, just writing the analytical formula doesn't work because this is it peaks to the 5½ power operation count, and we have n peaks of the order of 50 million pixels. So just doing this is impossible. So a lot of the R&D, the kind of thing that I was mentioning to you earlier, has been to try to find some tricks to be able to still do this. So for instance, you can, if you look at factorizable shape function, then you can bring this to something more palatable. Still, you can still not do it because, unfortunately, I mean, these estimators are actually for a full sky. Well, we don't have a full sky. We cannot measure things inside the galaxy. So there are all kinds of complexity, the noise being bizarre and so on. So in the end, we do Monte Carlo analysis of the whole process to be able to actually find the constraints. We've done this for all kinds of things, different estimators. So you can use all kinds of things like Minkowski functionals, skew spectra. You can use different bases. So we had a team large enough that we explored all of these various possibilities. And the reason for this is that all of what this is you are taking 3 fields and you each weight the triple product with different coefficients. So the only thing you do in the end is just having something that is more or less optimal, but is also more or less sensitive to various residual systematics. So by doing this, you're actually checking whether you can unearth some systematics. So that's the idea. And of course, there are some specific cases, like if you do strings, then you have to do some things dedicated to this. Now, there are sources of 3-point functions, and one of them is precisely due to the existence of lensing. And if you think of it, you have potential wells, right, that are creating the lensing, and this is also doing what is called the Sachs-Wolf effect, which is the fact that, I'm not going to get into this till the end, so let me just, you have to do enough to account for a number of additional source of 3-point functions, point sources and so on, as well as imperfection. But once you've done all of this, in the end, you can sort of compute these 3-point functions for it's L1, L2, L3, for if you correlate 3 temperature fields or 3 E-mode fields and so on. In the end, you weight all of this according to their signal to noise, and you get the final constraints. Okay, so I'm just giving you a flavor of the series of operations we do to actually get to the final number, like FNL local. Okay, the constraint is 0.9 plus or minus 5. That's the result. For equilateral configuration, which are generated in this manner, with the latest constraint is 26 plus or minus 47, which means that at the 1 sigma level, there is absolutely nothing. So all the game, and of course, the way to improve on this is to have more modes to be brought to bear on this. So for instance, yeah, it killed a lot of models. This is sort of, for instance, on FNL, this is something that we have been going as a community for a very long time. So you can sort of see that initially, say at the time of Boomerang and Maxima, the constraint was about FNL of the order of 2000. And now we are, I do 10 because this is 95%, so it's twice. So I give you these numbers. So again, this is a factor of improvement of nearly a factor of 100 in terms of constraints, constraining power, in about 15 years. Just a note, you sort of see how the constraints, what are the best fit value you obtain, as well as their uncertainty, as a function of the number of modes you keep. So at the time of WMAP, which was about at 600, there were hints of non-Gaussianity. But when you add more modes, more L modes, when you increase the sensitivity and the angular resolution of the experiment, you see that these were just fluctuations, and these actually settling nicely to 0. And this, in the end, is the plus or minus 5 that I mentioned earlier. So you have to add a large number of modes to do this. And the question is, how better will we be able to do in the future? Unfortunately, not that well. Because we already measured, we essentially extracted all of the information from the temperature mode. So what we're left with are the polarization mode. But we will not do more than the quadruple the quantity of information, which means that the error bars would be at most, and the improvement will be less than a factor of 2. Now, if you think, I'm anticipating a little bit, but for instance, for single field slow roll, the Maldacena bound is that the FNL local should be of the order of NS minus 1. So it's 0.1. So the target, to be nearly sure to find the residual level of non-Gaussianity that has to be present, at least for the most generic case, is very far away from, it's a factor of 100 further, 0.1, whether we are at 10 in terms of precision. And I just told you, we are very far of having the constraining power to be able to improve the constraint by a factor of 100. What we can do with a perfect CMB experiment is essentially a factor of 2. Which means that we have to find another source of information in cosmology. I'll go conclude on this. So that's the reason why there is excitement of sort of saying, well, what is the closest that we have in terms of, okay, so you want to go from 2-dimensional, where we've essentially exhausted things, to 3-dimensional. You go to the K-space, to the real space, I'm sorry, but 3-dimensional space. And you still want to have something that is understandable. So you would like to be as close to a linear regime as you can, because making predictions about with galaxy formation and so on. So that explains why there is excitement about the 21 centimeter thing, because it's a time, it's early in the history of the universe. So you think that the reflection in terms of the distribution, the observable distribution, is actually relatively easily related to the primordial one. still, to be able to do this, if you do a simple accounting of the number of modes, you want to increase the number of modes by a factor of, no, you want to increase the error bars by a factor of 100, so you want to increase the number of modes by a factor of 10,000. And essentially, this is a simple calculation. You need to, if you want to put antennas, you need to essentially cover the entire surface of the dark side of the moon. If you do this, which will take a little bit of time and money, then we could potentially get to the point where we could actually probe the Baldessina back, which would be really cool. But I might not be able to see this. I want to finish, if you allow a couple of slides which are just, you can look at the tri-spectrum, which is just the 4-point function. Again, you need to remove the lensing part and so on. So we've done this, we have the constraints, and you can sort of see that we improve things by another factor of 10, another 100 this time, as compared to what was existing. So in summary, on this, for the time being, this is the most stringent series of tests because we're really looking at terms which are, we have delta rho, delta theoretic of the order of 10 minus 5, and now we're looking at the square term of this. I mean, in the next order of the expansion. If you write this as a Taylor expansion, the phi is phi linear plus the term in phi squared. So now we're looking at, at the 10 minus 10 term as compared to, so this is really tiny, and there is just no sign. So in terms of inflationary scorecard, here I leave you with this. Essentially, the constraint on omega k, well, this is actually slightly anticipating, I'm sorry, this is already using BAO. So it's actually not what I should have done. Sorry, I just realized this. So far, I presented the Planck-only results. For this, it's not correct. I need to add some additional data. I'm sorry, I shouldn't have put that in. But for the rest, these are really Planck-only. And that sort of says that essentially all the generic predictions of inflation have been satisfied to high accuracy by the data. So that seems like a good place to stop. And yeah, that's just, increasing time of the precision and so on, and I think I'm really done. I hope. Yes, perfectly boring universe. All right. And I think I'm done for today.
So there is a recent paper from Majorana concerning this lensing anomaly and the fact that the Planck data could open the possibility of a closer to universe.
Yeah, I have quite a number of slides on this in what I hope to cover tomorrow. Yeah, but that's fine. I mean, so there are curiosities. Okay, so this is actually, so I give you one part of the picture, which is, there is really nothing that is really deeply significant. At most, there are things like a couple of sigmas, but things reaching the 5 sigma level, there is a deviation from NS. All of the others are much weaker significance. 0.1. So yes, you can look at a number of things. There are, for instance, and these are all the things that we looked at and found some significance at, a few sigma. I commented mostly about, where is it, power deficit at low L. That's what I showed you, the fact that L of 20, there was a dent, and I actually told you that's 2.9 sigma when you're at the power spectrum level, when you marginalize over the cosmological parameters and do the reconstruction of a primordial power spectrum, you get down to the 2.2 sigma. And yes, it's interesting, but that's still another revolution. Okay? So it's not the only one. There is a slight statistical power asymmetry between the two hemispheres. If you look at, say, power spectrum, but instead of doing it on the full sky, you cut it in two and you compare the two skies, and then you do this, you vary systematically at which equator you are doing this. And then you find that there is, yes, it's something significant at a few sigma. So what does it mean? Well, essentially it means that, yes, there is power on still larger scale than the observable horizon, which is not something so surprising, because why is it that inflation would stop at generating perturbation exactly at the scale of our observable universe. Of course not. And then there are other things like these. There is a cold spot, which is actually pretty significant, which is, yes, it's there, it's in the sky. There's just no question. We found that we cannot really completely explain it with sort of an empty void and so on. So there's all of these things. There is one thing that has been resisting our effort till 2013, is the fact that the smoothing of the peaks due to lensing is essentially a bit larger than one would anticipate in the basis of lambda CDM model. So, you remember I told you you take the image and you have this displacement field, okay, which is coherent over a fluid scale, but nevertheless globally the effect is essentially you blur slightly, the image you have. So the power spectrum, if you wish, the smoothing of the power spectrum is not exactly at the level that you would anticipate in the lambda CDM model. I will show you tomorrow at length the residual as compared to the best fit lambda CDM model. This is essentially what is driving all of the theoretical papers on all aspects. They are all proposing information on omega k, which is the Valentino paper, but not only. Okay, it's all trying to fit these low-level residuals as compared to lambda CDM in terms of L space. And all of the explanations that have been proposed are things which are essentially indistinguishable. They are just trying to fit these tiny residual as compared to lambda CDM. You can do this with W, the equation of state. You can do this with omega k. You can do this to also explain something that we also worked quite a bit on, which is a slight shift of parameters when you go from low L to high L. All of this is just fitting the same thing. So it all boils down of what is this lack of this extra smoothing of the peak. So we've been looking into this a lot because the most natural explanation was given all the fact. Okay, sorry, I'm sort of wrong. That's okay. I can do it without slides. Now we need a way to quantify this. The way we quantify this is to sort of say, well, instead of computing the smoothing of the peak with the actual potential that is within the lambda CDM model as fit with the other parameters, we'll introduce a consistency parameter, which we call A length. And so you assume that to compute the peak, instead of computing self-consistently in the model, because of course, when you do the calculation, right, you also include the lensing effect. What you can do is in the code, where you do this calculation of the CL, you can just increase by an arbitrary factor the lensing impact. Call this A lens. A lens is equal to 1 if you get the normal value in the model. Okay, so you have A lens. What Planck finds is A lens is about 1.2 plus or minus 0.1 typically, so a little bit less than that. So it's between 2 and 3 sigma determination of this A lens. I'm sorry?
Constant.
Yes, constant. You just say on every scale, I just scale what should be the value, 1. I mean, the theory value is 1. I just scale homogeneously this impact, right? It's just nothing else. So yes, we find that there is, if you want, an extra smoothing as compared to what is expected. Okay, so where is it coming from? It is a question. And so it could be a statistical fluctuation. It could be some it could be the impact of residual foreground. It could be a systematic effect, or it could be the sign of new physics. Okay, that's essentially all the possibilities. So we spend a lot of time trying to look at systematics and so on. One part could be, I mean, how should I say that? The minimal explanation, if you wish, is that this is a statistical fluctuation with a tiny, which is one part is due to a chance correlation with a similar feature on the dust template. But so how do you address this? Well, one way to address it is to look with other data than is non-Planck at different scales and so on. When you do this, you find that all of this other data doesn't want any of this new physics. Okay, you look at BAO, for instance, it says no. The omega k, the slight indication for omega k you find, BAO doesn't want it. And you can do for all of these other explanations. So if you want to stick to this explanation of new physics, you have to say that the other data, which is completely consistent with the lambda CDM model of this as done in the CMB, is wrong. That's pretty simple. Now, you don't, and it's worse than that, because we can compute the lensing also by doing this lensing reconstruction. This one, the CL55 that I showed you, is completely consistent with lambda CDM. So it's not lensing. Okay, that's a consistency error, okay, which we call A lensing because we have to boost. It's just creating a template which is the same shape than the extra lensing. We just know by direct lensing reconstruction that this is not that. Okay, so it's not lensing. BAO doesn't want it. Any of this extra explanation doesn't help at all, actually worsen the tension on H0. And you can look on supernova and that doesn't want it either. So you have a choice. You insist on being spectacular and ask for new physics, but then you have to throw all the consistency with essentially all of the other data sets, which is one option. Or you are using sort of some sort of Occam's razor and sort of say, well, the simplest is that I have a statistical fluctuation. And all of this other data is actually telling me, well, this was statistical, and when we want to have a full fit, everything fits together around lambda CDM. Of course, this is not a proof. And there might be, the future will tell. In the end, the only thing I can say, the future will tell. But I think this is more spectacular than anything else, given what we have. It's not the most economical way of thinking of it, which is exactly what Occam's razor is all about. Yes?
Sorry, concerning my first question and your explanation. All, for example, BAO data or other survey data are in a way considering a lambda CDM model, right? So my question is, how crucial is the choice that we do for the cosmological model? So is it the choice that we do at the beginning, no? So my question is, if everything fits inside the lambda CDM model, since we have chosen the lambda CDM model, or in some sense we can, do something independently on the cosmological model that we choose.
Again, I cannot quantify something that is undefined. The thing that I can do is take an extended model, which is not the basic lambda CDM. So let's look at the words, right? The base lambda CDM is a 6-pair. We are talking of extensions, and I showed you the Planck only. I didn't get into any of this yet. I showed you the strength of the constraint of Planck only on these extensions. And yes, you could see, well, let's just get back there. On this omega k1, let's see, where is it? Sorry, I'm getting back. Yes. All right. Okay, so if you look carefully, let's see where. Okay, omega k versus H0. You see that there is not a full breaking of degeneracy. I have some more on target this, but since you are asking now, I'm just doing it now. So you see that there is a strong degeneracy, and actually the center is slightly off. Okay, that's the strength of the evidence. Okay, all the business is, if when you look at this, the top of the best fit is actually not exactly on omega k equals 0. So there are, in Planck only, some indication at a few sigma level that the best fit is actually an omega k which is negative. Okay, that's this is the evidence that we're talking about. Just like any other, right? I mean, and W, it's even worse. Okay, yeah, look at W, it's even worse. You see that it's W of the order of minus 1.5 phantom dark energy is actually preferred to. Okay? Well, as I say, all of this are different signature of a residual as compared to the simple lambda CDM. These are just different explanations for fitting this particular small scale residual. Now, what do you do next? Well, I'm just saying, let's keep this open, but use another data set. And you would see that when you add this other data set, if it's devoid of systematics, it actually wants to have omega k very close to 0, and W equals minus 1. That's all I can say, is if this other data set is not completely affected by systematics, it says that this was a statistical fluke, and there is just no indication. But of course, you may want to take another course if you say, no. Oh, I don't want BAO, it's systematic. Because BAO doesn't want the omega. It really doesn't want it. I'll show you the evidence. I mean, it really doesn't want it. So you have to sort of say, I throw it out. So I have to throw out essentially all of the other data that is consistent within lambda CDM if I want to go into that course.
I think
that's all I can say.
We can
yes.
talk about this in this afternoon. I would like to see if there are other questions.
Yeah, but this one was anticipating that this was obviously the most, I was keeping this for the end, but I couldn't say, no, I'm not going to respond to you.
So we are honest.
So just a comment regarding non-Gaussianity. Maybe looking for the Landasiana result is conditions.
Yes.
In the sense that there are very interesting cases that one can learn by putting error bars of order L1.
Yes.
Because naturally one expects that you have to be order 1 if inflation is multi-field and the additional fields are spectator fields. So this
I completely agree. I'm completely with you. When I have a different cap and I'm actually defending other experiments, okay, in the future, that's exactly the point I'm making. That is on the way to this. Indeed, in particular, all multi-field model tends to have FNL of the order of 1. And so it's a completely natural target after the Planck step, which is, at 2 sigma of the order of 1 sigma of 5. You want to go to 1 sigma of 0.5. It's to try to see whether there is any early indications at a few sigma level. Ideally, the next target would be, we want to detect an FNL local of 1 at the 5 sigma level. It turns out that there is an accepted project to do exactly this. Okay, well, maybe I won't have to cover this anyway tomorrow, so let me say about this. Okay, so it's actually one of my former graduate students, that is the scientist on this. It's called SphereX. So SphereX is a satellite, mid-sized satellite project that has been recently accepted by NASA. It's the same class than WMAP was. And so what is SphereX? The most exciting goal of SphereX, in my view, is FNL. Okay, so it has plenty of other reasons, but so what is it? It's essentially something where it has some linear grading which allows to provide a low resolution spectrum in every pixel of the sky. And every pixel would be, I forgot, but that's sub-arc minute. Okay, I forgot whether it's half with an arc minute, whatever. So for every single pixel of the sky, you would get 100 spectral measurement. So it's a low res. I mean, Planck, if you want to think of this way, Planck was a 9 band spectrum. So this is a 100 band spectrum. And with this, so you can do all kinds of things with that. Study eyes, you name it. But one other thing you can do is look at the correlation function of the objects. And you look at the bispectrum. And when you look at the combined power of this, you find that we should be able to detect an FNL of the order of 1. Just because you have very small number of pixels, didn't say that one. You have very thin pixels, which means that you have a lot of modes that you can support on the sphere. It's as simple as it. So you actually do this progress of increasing the number of modes by a factor typically of 100 as compared to Planck, so you can decrease the uncertainty by a factor of 10, roughly. That's the only thing that I know of which has a fair chance to go there. I mean, this one isn't accepted. I mean, they are now building, and this is Olivier Doré, who has actually done all the sins and so on that compute this, constraint. And this is all due, oh yes, if you have a primordial non-Gaussianity like an FNL local, then you have a specific scale dependence of the bias parameter, which you can then translate into the spectrum and bias parameter. So that's a large scale phenomenon, it's a dependence. Without any projection, it's a little bit hard to, but that's still fine. This is accepted, and I think it's pretty standard thing. It's essentially computing correlations between objects and so on, or pixels. In my view, this is much more likely to give us some excitement than future 21 centimeter plans, because for them, right now, they are still fighting with the component separation problem of convincing us that they are really measuring things, at really early days, and that it's not some funny foreground fluctuations which are so much stronger than what they are trying to measure. So, I think from that point of view, this is the most exciting thing on the horizon, and that's exactly one of the big selling points of this experiment. Is precisely, we'll start exploring this range, which is very exciting. By the way, it's not only multi-field, but it's also all of this business of having non-trivial field space geometry, all the more recent development by Renaud Pétet and all of these guys. And so that's, I think that's one of the exciting things to come. I personally find that this is one of the most interesting things to do. So I cannot agree more. Thank you for this comment.
Any other questions?
Or comments, in particular, red ones like this.
I have one.
Yes.
Regarding this extension of the 6-parameter lambda CDM, Planck generally assume the Big Bang nucleosynthesis result on the primordial helium. Because the helium, the primordial helium is important for the recombination. What about this? In the sense that I have seen that in one of your transparencies you consider a possible extension with probably leaving free the parameter YP, the primordial abundance. But one could think that between Big Bang nucleosynthesis and the combination, the history is different from the usual, the simplest one.
Yep. Again, I mean, we as a team only explored, some aspect. The data is there. We provided the data, we provided the likelihood, and that's the cottage industry. People come up with new models, they fit, how they transform the predicted spectra, and then there you have it. So I think this is the next one. YP, it's here. So yes, this is a constraint. I mean, this one I did because it turns out that Eleonora was a postdoc with me at IIT, and actually some of the plots that you've seen are actually were made by Eleonora. The one in particular was a constraint on the volume of the parameter space. But we didn't do this for YP because it's a lot of computing time and so on. So I haven't done all of these various variations, but this is the one thing that is in the paper. These are current state of constraint. And in the coming time, you will see also how this compares with the other Big Bang nucleation constraints. It's normally tomorrow. Normally, I mean, tomorrow again, what I'm planning to do is confront, it's been Planck, but now I'm sort of saying, well, all right, what happens when we confront with other sources of information? Supernovae, VAO, VDN, H0, and, well, value the status. So that's the model, yeah. But I think what I wanted to say there, again, I'm sorry, but the omega effect does contain the VAO, I mean, this one. But what this thing allows to do is, we check for all kinds of other things, but the point that is important is, it's very hard to change the basic value of the parameters. It doesn't change completely what is the best fit for all of the parameters. It does change them a little bit. But the easy solution that one might have thought to sort of say, let's solve, let's say, the H0 crisis by introducing these extra parameters, essentially that doesn't work. And you can actually convince yourself by taking, the published likelihood or the published change and just do it for yourself.